Hello, everyone. No one on stage, because our next speaker, Sebastien Blandin, will be a remote talk. So I think he's in Singapore? In Singapore. So, okay. So you will hear the talk, and then you will be able to ask questions as usual, but he will be doing remote talking. Sebastien, you hear me? He's mute. Okay, so whenever you like.
happy to take any question.
Oh, thank you very much. So let's thank the speaker. So, time for some questions. Anyone? Okay, yeah. Here? Through the microphone?
Through the microphone.
Okay. Can you hear me? Oh, he's muted.
Yes, I can hear you.
Oh, okay. So, your algorithm, you tested the algorithm in urban traffic networks, correct?
Yes.
Okay, so I was wondering if your back pressure algorithm could be used for other transportation network, let's say, for example, railway transportation, which maybe will be characterized as under constrained network. Do you think your algorithm could be applicable to other transportation network like railway or any other transport means?
I mean, so the back pressure itself is redefined for a network of queues. So that's where physically it makes the most sense. For railways, I mean, so in practice, it depends if you can already, if the vehicles can already be stored at a given location and then given a green light, this type of thing.
Mm-hmm.
So I suppose, I mean, maybe, so if you consider typical flow models, which are used to approximate traffic flow for many networks, they are essentially a finite discretization of queues. So maybe back pressure could be implemented in this microscopic way, but I don't think it has been done.
Okay, thank you. Any question? Yeah, sure. Can you approach him? Yeah.
I just wondering, do you have any idea how to achieve smaller delay by using back pressure algorithm?
You mean smaller delay using the initial back pressure
Or any modified version of back pressure?
So in this work, what we try to show is that you can have smaller delay if your objective function is a better approximation of the actual delay in the network, right? So that's what we try to do. And I think it's sort of a promising approach because, I mean, numerical results seem to indicate that it works. Yeah. So other ideas, I mean, I don't yet have other ideas to improve further, but I think this one seems to work. I think so.
Okay, so let's thank the speaker again. Thank you, Sebastien, thank you. No, this works. Okay. Thanks. Que gracias. Okay.
Hello? Okay.
Okay. So, we now go to the last presentation of this session, which will be presented by Hsu-Chieh. And you have here the title of the talk. So.
Good afternoon, everyone. Thanks for attending the last session in the last day. And I'm Hsu-Chieh from Carnegie Mellon University, and this is a joint work with my advisor, Stephen Smith. And the title of our work is Using Bi-Directional Information Exchange to Improve Decentralized Schedule-Driven Traffic Control. So as we know, traffic congestion is a very serious problem now, and it's so very universal. And the congestion costs United States city over $160 billion in time and fuel. And if you drive your car every day, you probably spend more than 40% of your time on street idling. So actually, it's a serious problem, and we want to know, can we apply planning and scheduling to solve this problem? And one of the reasons for this problem is that our intersections are still not smart enough. And the current traffic signal control system is only optimized for the average traffic condition. Yeah, we just take an average over a certain time. And the way we use in sensor or detector is only for detecting the stopped vehicles. So this schedule-driven traffic control is a new approach to deal with those problems. And it's a real-time system. That means it doesn't rely on the average traffic condition. It's just compute the timing in real time. And this approach has three main components. The first one is the cluster representation. So we just cluster those consecutive vehicles into one cluster. So after that, we will have a sequence of clusters with different size. And after that, we will input this sequence of clusters into our solver by solving a single machine scheduling problem. And after that, this intersection will communicate this produced schedule to its downstream intersection as a way to do the prediction. And the downstream intersection will combine the local detected clusters and the non-local cluster received from its upstream intersection. And then, based on these clusters, and produce a corresponding schedule. And this whole process will be applied every second, by applying the replanning technique. So that we can deal with the uncertainty of the traffic condition. So here I use an example to explain how it works. So considering we have a two-phase intersection, and the phase one, we have a sequence of clusters, and similarly for the phase two, we have another sequence of clusters. And then we define the state, and then by transiting different state, and we can produce a schedule to minimize a certain objective function. And here, the state includes the phase and phase duration, and end time, and the cumulative delay. So if we take cluster 2, 3 as an example, it's a phase, is phase 2. And the phase duration is the summation of these two blue clusters. And also we will know its end time, and also we will know its arrival time. And after that, after schedule, we will know its actual starting time. So by transiting a different state, we want to compute a schedule to minimize the cumulative delay here. And the delay for each cluster is a number of vehicles multiply the arrival time minus the actual starting time minus the arrival time. And this approach, we already deployed this approach in many cities, around the United States, for example, in Pittsburgh and Atlanta. And we do observe some problem, So the problem is that can we provide better network coordination, especially for saturated network? The the approach we just mentioned performs very well for the medium and the low demand traffic. But for high demand traffic, we want to know, can we provide another solution to solve this problem? And for saturated network, usually we will have a large platoon, and the large platoon will cause the spillback effect and also the gridlock effect. So we found that the efficiency of the schedule-driven traffic control varies across different traffic demand. And we want to know, can we provide a new coordination scheme to adapt to different traffic demands? So here, I introduced a new type of optimality here. Imagine that if you drive your car every day, when crossing a certain transportation network. What you really care about is how much time you spend when crossing the entire network. So the question will be like, can we enable more information exchange between intersections to achieve this kind of optimality? So here's the intuition. If we have two intersections here, and the intersection one now need to decide whether to send this red vehicle now or later. And we know the intersection 2 will switch its phase after 4 seconds. So if the intersection 1 sends this red vehicle now, and the current waiting time in the intersection 2 is 10 seconds, and the total delay for this red vehicle is 10 seconds. And if the intersection 1 wait for 5 seconds, and the intersection 2 already switched the phase, and now the waiting time is only 2 seconds. So the total delay is 7 seconds now. So obviously, if we want to minimize the driver experience for this red vehicle, we should go with the second choice. Considering a more extreme case here, if the intersection 2 is pretty congested, and we probably won't send any vehicle to the intersection 2. So here, I want to introduce the problem formulation. As I mentioned in the introduction, each intersection will have a local cluster and a non-local cluster, which are received from the neighboring intersection. And then each intersection just solves the individual objective, which is the cumulative delay. And now, if we want to approach to the new optimality I just defined, and so we can define a new global objective here by just summing up all the individual objective function. So we want each intersection to compute a schedule to approach this new optimality. However, to solve this new global object optimization problem is unfortunately is intractable, especially for a real-time system, because so now we introduce two assumptions here. We assume the impact of the traffic are local to the direct neighbor intersection. And also because we apply replanning every second, so the traffic at time t is not deviated too much compared to t-1. I will explain more about these two assumptions later in the next slide. So now we know for a transportation network, we have this global optimization problem, and we want, especially for a decentralized system, we want each intersection to make decision and approach this new optimality. And for the original schedule-driven traffic control, each intersection just compute the schedule based on the individual objective independently. And but now, if we want to approach this new optimality, we will have to modify the objective for each intersection. So by introducing the additional term here. So which is actually the impact this intersection impose on the neighbor intersection. And by introducing the two assumptions I just mentioned, we can reduce the problem, we can relax this problem to a simpler problem here. So we just assume the direct neighbor, and also we assume we have the previous schedule from the neighbor intersection. So now we just need to compute our own local schedule by solving this new problem. So this new term, you can take it as like a price or tax when you generate a certain schedule, and that's prevent the schedule to hurt other intersection. Okay, now how we realize this idea in our system. Yeah. So as I mentioned in the introduction, the cluster delay is the original cluster delay is defined in this way, and now we extend the cluster delay from the single hop delay to a two hop delay, which means that we extend the cluster delay from single intersection to two intersection. So now we need to know the expected next hop delay. However, to compute the exact next hop delay is really difficult, especially for a real-time system, because we need to expand our state from single intersection to two intersections. And also, because we apply replanning every second, so the communication overhead is another problem. So basically, we don't think it's possible. So here, we propose a simpler method to deal with this problem, which is called congestion feedback. For each intersection, it's well known the current schedule. And based on the current schedule, we can compute the average delay for each vehicle on phase 1. And also we can compute the average delay for each vehicle on phase 2. So after that, so if this intersection want to send this green vehicle to intersection J here, and the intersection J can feedback the congestion feedback to its upstream intersection. Similarly, for the intersection K, it can also compute the average delay for single vehicle back to the upstream intersection. So if these two numbers are comparable, we have this kind of schedule. And if the green number is greater than this red number, we probably will serve more red vehicles instead of the green vehicles. So here, I want to use this slide to summarize our algorithm. So at the beginning, each intersection will receive the congestion feedback from its downstream intersection, and also will receive the non-local cluster from its upstream intersection. And then we apply the forward recursion dynamic programming to compute the schedule. And after that, when we have the schedule, and we will send our computed congestion feedback to the upstream intersection. And also we will send our computed schedule to the downstream intersection. And this whole process will be repeated every second. So here, I want to show some simulation results. And we consider a two-way queuing grid network. And the traffic pattern we test here is the PM rush hour. And we use the vSync to evaluate this idea. And we compare our algorithm with the original schedule-driven traffic control and the SCAD system, which is actually a very popular traffic signal around the world. So we can find that our proposed algorithm can reduce the delay by 13% on the 90% of the congested vehicle, delay vehicle. And if the bottleneck criterion is it's a way to jump out of the local optimality. So if you are interested, you can refer to our paper. So we can see that actually the schedule, this new extension can help schedule-driven traffic control to achieve a better network coordination. And also, we record the number of stops during the simulation, and we found that by applying this new extension, we can reduce the number of stops very much by like 5 to 10%. So which means when you drive the car, you can get a more smooth driving experience. Okay, so one of future work is that currently we just very intuitively apply by compute the average delay for each schedule. Yeah, but if we can provide a way to estimate the next hop delay in a more precise way, we probably can improve the performance for medium demand and low demand. Currently, it's just improved a lot when we have a saturated network, which is the high demand. So the conclusion is that the real-time scheduling or planning require adaptation to the traffic conditions. And to ensure the scalability and optimality, we need to find out a way to decide the multi-hop information. Yeah, so that we can achieve a better network coordination. Yeah, thank you for your attention, and I would like to take your question. Thank you.
We have time for questions. Any question? I was wondering whether the level of congestion in the traffic situation affects the size of the clusters. Is it that, or is only the schedule that is being affected by the level of congestion? How does it affect the cluster size?
Yeah, when we have a less congested scenario, and we do observe a smaller clusters in the field, on the road. Yeah, so that means that our scheduler can compute the schedule very efficiently. Yeah, however, sometimes, when the traffic becomes congested, due to the clustering, we encounter some problem here to degrade the efficiency of our scheduler.
And I guess this also affects the number of stops. Right. So
right.
The higher the level of congestion, the fewer number of stops that you can address.
Yeah. So it can fix like the spillback effect. That means if your downstream intersection already congested, you probably won't send any vehicle to that intersection. Yeah, because that will make the thing worse, right?
Yeah. Thanks. Any question? Okay, so let's thank the speaker again. Thank you.